morning, everybody. Welcome to the PO.DAAC and Open Ocean of Remote Sensing and In Situ Data for Science in the Cloud Earth Data webinar. That was a mouthful. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started here. First, what I'd like to do is go over a few webinar logistics. To ensure the best audio experience, participants have been placed in silent mode. But please do be sure that you have your microphones muted or disabled. We are recording today's webinar, so that really helps. If you have any questions, if you have any issues, what I'd like for you to do is enter those into the Q&A pod. You'll find that located on the right-hand side of your screen. And this works like a chat. Today's webinar is being recorded. The recording will be posted to our online Adobe Connect webinar catalog as well as to our NASA Earth Data YouTube channel within a few days of completion. Once completed, I'll send an email to all of the registrants with both of those recording links. As far as timing is concerned, today's webinar will be 1 hour long. Somebody needs to mute themselves, please. With 45 minutes allocated to the presentation and an additional 15 minutes for the question and answer period. During today's webinar, we'll have 3 speakers. I'm actually going to pull up the agenda at this point. Our first speaker is Ed Armstrong. He's a Senior Science Systems Engineer at NASA's Physical Oceanography Distributed Active Archive Center, or PO.DAAC, and that's located at the Jet Propulsion Laboratory. He will begin today's webinar with an introduction to the NASA PO.DAAC and its data holdings. And then from there, we will transition to our second speaker, Jessica Hausman. Jessica is a support scientist for the Physical Oceanography Program Office at NASA headquarters. And she will provide a NASA perspective on open data for open science. When she's finished, we'll toss it back over to Ed Armstrong for an overview of the new cloud-based missions and cloud services at PO.DAAC, and then he will provide a live Jupyter Notebook or Python demonstration showcasing some of the ways that you can discover, access, and also work with physical oceanography data in the cloud. So once we've finished with our live demonstration, we will transition to our final speaker for today, Dr. Jorge Vasquez. Jorge is a research scientist at NASA JPL. He will wrap up today's presentation with a discussion of in situ data sets at PO.DAAC, including some of our field campaigns such as Saildrone, SPURS, the OMG mission, and then he'll talk about connecting these observations to scientific research results. After Jorge finishes the last segment of the webinar, we'll move to a final optional set of polling questions, and then usually I'll give these, 3 or 4 minutes or so. And then from there, we'll move directly to the Q&A period. And depending upon the volume of questions we receive, we'll extend the Q&A period an additional 15 minutes from end time for those of you who wish to stay on the line. But we will have a hard cutoff at 3:15 Eastern Daylight Savings Time. Okay, and so just one final point. During today's Q&A discussion, we'll try to answer as many questions as possible during the time allotted, but if we do not get to your question, our speakers will follow up with you offline after the webinar. With that, it is my pleasure to introduce today's first speaker, Ed Armstrong, and I'm pulling up the slides here, Ed, so hopefully you can see those.
Yeah, there's things like they're still loading. Welcome, everybody. This is Ed Armstrong here, and I'm going to be the first speaker, as Jennifer mentioned. So next slide, please. A little bit about the PO.DAAC. I'm sure many of you already know this, but just kind of review that for the Physical Oceanography Distributed Active Archive Center, one of the 12 NASA data centers for Earth science data across the United States, responsible for archiving and distributing Earth science information products, primarily satellite products. And of course, our mission is preserving NASA's ocean and climate data and making those universally accessible and meaningful. The other 11 DAACs that you see there on the map, they cover other disciplines such as ocean color, the atmosphere, as well as snow and ice, and a few others as well. So we have, the PO.DAAC has about 600 publicly available data sets and growing, about 0.5 petabyte of data in our archives. But the point of this of this seminar is to, inform the user community that a number of new missions are coming online that'll be cloud-based, and really the data volumes are growing quite larger. And so, hopefully by the end of this seminar, we have a little more certainly more familiarity of what those data sets are, and that some of the tools and services that allow users to operate on these data in the cloud. Just, a reader what the PO.DAAC is responsible for. You see the little icons there about the gravity, salinity density, ocean temperature, circulation, sea surface topography, ocean winds, and surface water. So these are the disciplines or the variables that we focus on in our particular data center. So next slide, please. And I don't think I'll dwell too much about this. Jennifer gave a nice introduction, but we will have 3 topics. One of them by Jessica Hausman on introducing open data and open science, kind of some NASA focus emphasis currently. And then I'll be coming back to talk about these new cloud missions, the 3 that are listed there, as well as run a little practical Jupyter Python recipe that will exercise some of these cloud services and actually show how to build essentially what's a data cube. And then our last topic, we'll be reviewing the PO.DAAC in situ data sets and looking at some interdisciplinary science from this perspective, including in situ data sets, any of these missions such as Saildrone, SPURS, OMG, and S-Mode, and Jorge Vasquez will be leading that. So I'll pass it back to Jessica. Thank you.
Thanks, Ed. So I'll get my part open. So as Jennifer and Ed has stated previously, I support scientists for the Physical Oceanography program. I work with Nani Benegredova-Schoffer there. And so I'm going to talk to you about kind of this perspective that NASA is taking on open sciences and open data, and then how it ties in with the PO.DAAC, and then Ed and Jorge will take it from there, and you'll be able to see how everything ties together, hopefully. So first, I'm sure all of you have heard the term open science by now, but in case you haven't, or it's still a new concept, open science is basically breaking down the barriers to enable science. Those barriers can be anything from being able to access the data. So all the data from NASA are free and available. PO.DAAC is the Physical Oceanography archive for that. So you can always grab NASA data. Other things are being able to process data. So that's part of the reason why NASA is moving to the cloud for its data holdings. It makes accessing the data easier, especially with the volumes that are coming up with the newer missions. There are also things like other parts of open science, such as accessing journals in order to share knowledge. There are some, in the university communities, they're talking about, which publishers do they want to buy subscriptions from and such, because do they support things like open journals and reduction of paywall barriers. Also in how you do your coding as well, because things that are like Python are open licensed, and so people are moving to that as well. So now you can access your data, create your software workflow, and share it with your community with as few barriers as possible. But that knowledge that you have of your community, of your science, that is still yours. But you are now able to share that with the community and make the community grow stronger because of it. So why open science? So I already touched upon these things, but to help enable science, I am sure a lot of you spend a lot of time wrangling data, just trying to access the data, convert it into a format you need it in, so that you can finally actually do analysis on it. Hopefully with the open science, that reduces those barriers because you can now share your code for your data wrangling along with others. So you're not reinventing the wheel every single time you need to, like, let's say, regrid from one grid to another grid. Make sharing information easier because now you have software and data repositories. A lot of journals are also requiring that you share this information as well. When you share it, because it is in a repository, they typically have a system for putting a digital object identifier, or a DOI, which is that unique code that you have with it. It's the same as the journals. So now you're actually able to cite your software and your code and your data. So there's less discrepancies as to like what version you used. It makes it clearer, and it's much easier for reproducibility. And it makes analysis analyzing the data easier, because now you're not necessarily subjected to staying at your desk. I'm sure everyone has realized this past year we're able to do a lot more things remote because we aren't tied down to specific servers necessarily. And it also helps too if you're out in the field. You don't have to necessarily be tied to a laptop or excuse me, a desktop anymore. You can pre-code everything. Excuse me. You can do all your code ahead of time and then access it with a cell phone. So it's great for when you're in the field, when there's a disaster, first responders, or even if you live in an area where like you don't have stable electricity either, you can reduce those barriers and still be able to get the information you need. So what is NASA Earth Science doing with open science? So first of all, if you want to find out what's happening, that URL on the top at earthdata.nasa.gov will give you the latest information. So the ROSES calls, which are basically the proposal calls that NASA puts out, they are now requiring that data and software management plans are included. You can also, when you write your budgets for publications, you should budget for the open access publication prices. They are a little bit more, but that means that anyone can access your articles now. And then, so you reduce paywall barriers that way. As I said before, all data from NASA are freely available from the DAAC. There is a project right now called Earth Data Cloud. That's going to be the new data repository for all the DAACs. And the great thing with that is that all the DAACs are going into the same cloud, so now you can share data from one DAAC to another as opposed to going you can still go to each one's individual websites, but they all tie in the same area eventually. So it makes it a little bit more like one-stop shopping. Software and tools are also available that were designed for the search and access of data. They are put up into a repository, to a NASA repository where you can access that as well. And there's also this hub space which NASA is using, and it's encouraged with the Earth Venture missions. But if you are a NASA-funded PI, you can use that as well, so you can upload your article along with all the data that you use for producing your tables and plots and things like that. So it's all in one place, because the journals don't provide that for you. So how does specifically the physical oceanography program support open science? So as Ed will talk about later on, there's ECCO and Sentinel-6, which are moving into the cloud. These are very large data sets, but now you can access them directly through the cloud and hopefully be able to analyze it quicker with your code near the data as well. And after SWOT launches, that will also be in the cloud. It also allows you to use multiple data sets that might be available from the other DAACs as well. Our proposal calls are now actually stay in there as an open science requirement. It was in the past call for the Ocean Surface Topography Science team, and it is in the next upcoming call for the Ocean Salinity Science team, where you, if you produce certain products, you need to abide by open science. Several of our PIs are members of Pangeo, and if you want to see how a community does open science, Pangeo is an excellent example. There's their website to check it out. And of course, PO.DAAC. PO.DAAC has been fantastic with sharing their data, sharing their code, and creating material for how to use the data in the cloud as well. And it's going to give you some demos on that. So with that, I'm going to turn it, oh, sorry, I have one more slide. So PO.DAAC and open science, of course, as I said, they're doing a fantastic job. They already get the Sentinel-6 and ECCO data in there. They also have a GitHub repository for their the code that they're developing, and also the Jupyter notebook, which you can find in that GitHub spot as well, where you can see and actually, start doing some things hands-on. Right. With that, I'll turn it back to Ed.
Thank you, Jessica. So I'll introduce you to these three new cloud missions and services. And so it's important for the community to realize again that these new missions and actually missions going forward for the PO.DAAC will all be in the Amazon cloud. Specifically, that's the Amazon Web Cloud, the Amazon Web Service. So the first one I'm going to introduce is ECCO. That's an ocean model, stands for Estimating the Circulation and the Climate of the Ocean. And it's a full three-dimensional circulation model built on the MIT General Circulation Model. And it's not an operational model. It's a retrospective model for climate studies. And it's a multi-platform, multi-instrument, multi-variable synthesis product that really integrates a number of ocean and ice observations into the model. So we see there's a suite of satellite observations for altimetry, SST, salinity, and ocean maps from that suite of satellites you see there, as well as a number of in situ observations from things like the Argo program, ships of opportunity, and even marine mammals that have little CTD sensors on them are used to both assimilate and constrain this model. So as I mentioned, it has a fixed period from 1992 to 2017. It has 50 levels. Of course, being an ocean model, has all manner of ocean variables available to the user, including temperature, salinity, currents, as well as potential temperature and density. And then it has a full suite of atmospheric fields as well, specifically the momentum or the air-sea fluxes for heat, moisture, and momentum are available. There's a number of grids that it's available on. The most probably user-friendly grid is this equidistant or the 0.5 lat-long degree grid, both globally, and there's a specialized one for the polar. It also has this native grid that you see there in the lower right-hand corner that essentially breaks up the world into a suite of tiles. So the model is monthly with select mean daily fields, and it's about a total of 7 terabytes of data. So not a huge amount of data, but yeah. And what else? So this particular data set is on the imminent release. So it will be released publicly. All 75 of the data sets for the ECCO mission will be released publicly in the coming weeks. So it's quite exciting that we'll really have one of the first public data sets available in the cloud. But predating this, we actually have been ingesting data from the Sentinel-6A, the Michael Freilich Jason CS mission. This is a collaborative mission, kind of a continuity altimeter mission in collaboration with ESA. This instrument was launched in November of 2020, and actually we have been ingesting data into the cloud. This particular data set provides the high-resolution sea level topography measurements. As I say, this is a continuity measurement mission that kind of building on the data from the original Topex's Poseidon mission in 1992 and continuing on with Jason 1, 2, and 3. So it is a very quite exciting data sets. There'll be about a 50 total data sets. You see the listing there. You actually can go to our website and look at them right now. But the data is actually still in its CalVal period. So the actual public release of the data sets won't be until later this year, probably at the end of the summer. And let me see. Yeah, I can kind of like to highlight here some of the more popular data sets that we expect from this particular mission. Here's the level 3 ocean topography data. This is all in NetCDF, as well as there'll be a level 2 as well. And in addition to sea level or ocean topography, it'll also give information on the significant wave height. So it's often used as inputs into operational wave height models as well. Now we have a number of tutorials that we've written or Jupyter notebooks that are available on our GitHub site. You see the URL right there. They're essentially data discovery recipes using some of these NASA cloud services that I'll describe in a little bit more detail a little bit later. So the final one I wanted to, I guess the animation doesn't appear, but I want to introduce the SWOT mission, the Surface Water and Ocean Topography. This is a very exciting new mission, interferometric altimeter mission that will measure global ocean surface topography and land surface water elevation with really great accuracy and spatial resolution using interferometry. So it's a little bit different than the NADAR altimeter that I described for the Sentinel. And on the ocean side, it's going to be used to characterize both the meso and the sub-mesoscale circulation. And there we see a little image there, demonstrating Well, you know, what you can see at the mesoscale, and then when you go all the way down to the sub-mesoscale, like 10 kilometers and below, you can really see these really fronts and 80s in much higher detail. So the launch for this particular mission has always been pushed out for various reasons. We're looking at now sometime in 2022, but it'll have a tremendous new total volume of data coming through, 60 petabytes. And as you mentioned, so I mentioned at the beginning of the presentation, the PO.DAAC really only has about half a petabyte right now, so it's going to be a tremendous explosion of volume. Besides the science objectives in the oceans, of course, there's some other applications that this will be extremely useful for, including flood and drought monitoring, water resources management, inland and coastal commerce, coastal zone management, and climate and weather. So because of this thing has a wide swath and still has very high spatial resolution, we'll be able to get at things like lake elevation and even be able to see in very wide rivers. So there's a number of new exciting hydrology applications that will come from this particular mission. And unfortunately, I had a little animation there that doesn't seem to want to play, but I'll move on to the next slide. It seems to be stuck. Okay, yeah, this slide just demonstrates the PO.DAAC archive growth over the years. It's a little bit out of date, maybe 6 months out of date, but as you can see there with the red bar, once we get past the red bar and start ingesting these new products and data streams from the SWOT and the Sentinel-6 mission, we're looking at an exponential size in the growth. The left-hand axis is actually on a log scale. So within a few years, you know, we'll have several tens of petabytes of information, primarily driven by the growth in SWOT and Sentinel-6. That's the green plot there. Versus the blue plot is, you know, the kind of the historically driven growth from existing data sets, you know, much lower size, only 1.8 petabytes. So essentially, this is one of the reasons that's driving these new missions into the cloud from the perspective of data management. And commensurate with that, NASA has developed a whole ecosystem of tools and services that I'll be demonstrating that allow users to operate on the data just within the cloud. So this is a kind of a new paradigm shift from the perspective of the user. Will they'll actually be operating on the data, preconditioning the data, doing things like subsetting, other types of operations on the data before they actually download it, with the idea that these conditioning steps that are very, very easy to do once all the data is located in the cloud. It'll free up more time for the scientists to actually, or the application users to actually do more science and do more utility with the data versus spending a lot of time, conditioning the data and downloading the data. So I think that's my final slide. I have one more slide just kind of demonstrate some of these ideas of how a user is going to work inside the cloud in this new kind of paradigm. So there's the user down below, and he's operating on the data inside the cloud, using all these tools and services that allow him to discover granules and operate on those granules, do things like regridding or visualization or other types of transformation, and then downloading finally those products down to his local computer or his local server. And the point here, there's the little arrows that all these operations that you do in the cloud and the downloading, that's all free of the user, so that's all on the NASA dime. The user doesn't have to worry about those costs at the moment. Again, the capabilities we're looking at are reprojecting, regridding, reformatting, subsetting, doing some time series analysis, things of that nature. So that's my final slide. I wanted to demonstrate now some of these capabilities. I think I had last week to go back to the services. I was going to, there is one more just like slide. I actually got to show, demonstrate some of these services operating on the GRIS-MODIS Level 2 sea surface temperature data set. This is a very popular data set, 1 kilometer SST resolution. And we're going to be using what is known as the NASA Harmony API. So this is essentially the name of this ecosystem that exposes all these nice services to the users. It allows them to do, allows them to do things like the subsetting and the transformation, and there are other services behind the scenes that actually do the discovery of the granules and things of that nature. So we're going to use some of these services on this particular data set to perform some of these operations. And essentially what we're going to do is we're going to find some granules, transform them, subset them, transform them, and then stack them in a nice little data cube. And then just use Panoply, which is a very popular user, to look at the output. So I'd like to share my screen now. And I'll share my screen. And I think it's loading. I'll share the main display. And I'll just open my little Chrome browser here, where I have a little Python notebook set up here. And the title of this thing is the Analysis Ready Workflow for MODIS Aqua L2P SST Collection. So it has this is a Python Jupyter notebook, and it has a bunch of code blocks in here. Some of the initial code blocks are just simply handshaking to kind of set up your session inside the cloud where we pass our NASA credentials. It looks like it's a little complicated.
Can you make
Sure.
this full screen, please? We can see your desktop underneath and so forth. Thank you.
Ah, okay. I mean, is that a little bit better? Or is that a little bit better?
That's definitely better. Thank you so much. Perfect. Sorry
Yeah,
for
maybe
the
I'll
interruption.
magnify it a little bit more. No worries. So again, these two code blocks are just kind of setting up the handshaking to basically log in with your NASA credentials. It sounds like it's a lot of work to do, but basically it's not that much. You just execute it. If you're writing one of your recipes by yourself, you just kind of cut and paste this code block and you just execute it and you just do it. So that's the first couple code blocks here. The next code block just sets up some constants, sets me up a little download directory, endpoints for the root directory for Harmony, and now I'm actually going to execute the login. So I'm successfully logged in. It didn't come back any errors. If I had wanted to get what's known as a token, a CMR token, to make a query on the CMR, which we're not going to do in this particular recipe, you would execute that. So here's the main part of the workflow. So we're going to discover some MODIS granules within a region of interest, make a spatial subset, and then remap those subsets to a common grid, and then aggregate those output maps into a data cube. So all the images will be co-registered. The point here is that I'm working at the original data is level 2, so that's an ungridded data set, right? It's not all the files are not on a common grid. They're all slightly different. They're in the satellite SWOT coordinates. And the point here is we're going to take those and regrid them, georectify them into a common map. When you work with these data sets in the cloud, you have to know what's known as the concept ID. It's this little kind of cryptic ID that you need to find by doing a search on the NASA Earth data search. But once you find that little ID, you just use it, right? It's just a static ID that points to this particular collection in the cloud. There's a start time, a temporal bounds here. I'm just going to do like over 3 days here in July of 2020, just because for time's sake. And I'm going to be looking subsetting over a region here in the Hawaiian Islands. So I'm going to run this code block, and the next code block is actually executing this Harmony engine, right? That's actually doing the subsetting. I'm just going to execute it because it does take a little time for it to run and just explain some things. So what this little code block here does in this little Python dictionary is just kind of passing these constants into the Harmony URL that we're going to form right down here. And it's really quite elegant because what we're going to do is actually pass in these lat long bounds that I just defined in the config file, as well as a start and stop time. And all in one operation is this information going to be passed to Harmony, where it's going to go and find these particular granules and do the subsetting based on these space-time bounds. So it's all really in this one URL that encapsulates all the information of what I want to do the actual subsetting. So the job has executed. It dumps out some information that it has processed. It did find 9 granules. Here's my username, so that's me. It actually has like a little job ID, so we can kind of see what's going on with the job. And actually, if you execute this URL, it'll tell you what's going on with the job. We're going to parse the output of that. It's just the JSON output. It's going to tell me a little bit about what it's been working on. And so here it's been creating these little subsets. And so again, this Harmony service is taking those MODIS inputs and creating these little subsets and just storing them in a little ephemeral location on the Amazon cloud that I'm going to download in the next step. So it looks like it's pretty much done. It is done, right? So that was pretty quick for those 9 granules. Now I'm just going to download them to my local computer. This will also take just a brief amount of time. And then I'll get on to the next part, which is actually I'm on my local computer now, and I'm going to be using things like GDAL, which is the geospatial data extraction library. It's a very powerful library to do reprojection, regrading, reformatting of the data, as well as I'm going to be using the NCO toolkit to kind of clean up some of the artifacts that the GDAL leaves behind. So it looks like all my files have downloaded locally to my system, and I'm going to start executing the rest of the script. Sorry about that. Let me make that a little bigger again. Hopefully you can see that. So again, this part of the script is doing the GDAL, which is actually taking these level 2 outputs now and doing the regrading to a common degree, into a common map. So it's kind of just remapping all the pixels using an interpolation scheme. And it looks like it's done with that. And so next step is just using NCO to kind of do a little bit of house cleaning, a little some of the metadata and variable stripping, the little artifacts from the GDAL step. But it all works really quickly here. And so that step is done. And now we're actually going to create this little data cube. So we have all the output files, level 2 output files. We regraded them into a level 3 and done a little packaging with the NCO. And now we're actually going to use NCO to kind of aggregate them all together, and it's done. So let's go ahead and look at that. I'll get my terminal window right now where this is my little output, local output file, output directory, and these are the files that were created. So these were all files that are created by the Harmony subset service that I downloaded. And then these were all the files that my little GDAL and NCO operations created, or actually the regrading step. And this is actually my little output file. So let's have a look at that. And I'm going to open this in the Panoply Data Viewer. It's a viewer that I like to use for looking at NetCDF outputs. And so here's the output. I actually only outputted 2 variables from the input file, the actual SST measurement and the quality level. So if we look at the SST and just do a little plot it up a little bit to get it going here. So Panoply recognizes all this, and there's our first little output there. And let me zoom up here. So here we are of the Hawaiian Islands. What we see here in this particular file is now these little 7 granules. There were originally 9 granules, but I think a few of them got dropped because he actually didn't have any data in them. But here are the 7 granules within that 3-day time period that were found and aggregated to this little program here. So again, not every overpass of MODIS will have data in the whole region of interest, right? But as we kind of scroll up here, and this is the second image in the stack, and the third, we see that they're all there. Of course, this is just the SST. It's not been screened for clouds. So we do see some clouds artifacts here. The yellow and blues are certainly clouds creeping into the signal right there. But the point is that they're all lined up in one grid, and for if we did this over like a month or a year's worth of data, it would take longer to run, of course, but we will have all this data nicely locked up in a single stack where we could drill down at a single lat long and say do some time series analysis or some matchups with buoys or ships or things of that nature. So kind of cool. Just a way of getting some level 2 data into like an aggregated level 3 grid was the point of this particular recipe. And I think if I go back to my recipe right here, there's one kind of final step I wanted to show you, just kind of like a little simple plot here. This is a plot of a single point in the grid here. The top shows the unfiltered data, so there were 4 little points here. This is a histogram of the entire region of interest. And if we screen that information using a quality level of 4, so there's 5 quality levels. 4 and 5 are really the best data for these MODIS products. So we're doing a 4 and 5. And we see we drop out with 2 points, but the histogram really cleans up. And so all that cloud contamination that you saw in that stack, right, I mean, it's very easy to filter out those extraneous observations from the final product. All right, well, I hope I gave you, a good introduction to these services, and of course these recipes are available on our GitHub site, so you can download them. I mentioned the Sentinel ones, but a number of other recipes that have been written, including this MODIS ARD one, that are available for the public to use. And I think I'll stop right there and pass it over to the next speaker, which will be Dr. Jorge Vasquez. If I can find my my Adobe Connect again. There we go. So thank you all.
Can you hear me?
I can, thank you.
Okay, thank you, Jennifer. Sorry about that. Thank you. I want to, for the third topic, thank you, Ed, is looking at remote sensing and in situ data, and I call this a necessary partnership. And I really want to thank also Yibo Zhang and also Vardis Santos, who, Yibo did the animations that I'll be showing, and Vardis Santos has actually shown incredible leadership with the SPURS, getting the SPURS data into the PO.DAAC, which I'll talk about also, and leadership and in situ integration also. And one of the reasons that, I just want to say from a historical perspective, the PO.DAAC has actually been involved with this issue of in situ integration and remote sensing, I think, since almost the very beginning. And just to give you a little bit of a historical perspective, we were involved with the NOAA-NASA Pathfinder Sea Surface Temperature Project, which was a reprocessing of all the NOAA advanced very high resolution radiometer SST data. And the PO.DAAC actually also, at that time, also distributed the matchup database associated with the algorithms and all the calibration of the SST data. So this has been a progression, and I think, as I say, it's been a necessary partnership. And I'll show you also an example of this from the ocean melting Greenland, because it was a what I think is a breakthrough paper that was just published on this subject. So just some examples of PO.DAAC supported in situ data, and this also came out of the launch of the Aquarius satellite and also the Soil Moisture Active Passive mission. And this, there were 2 field campaigns that supported those missions, as well as the science, the Salinity Processes, and the Upper Ocean Regional Studies. That was 1 and 2. SPURS 1 was actually focused on a high salinity area in the North Atlantic, and SPURS 2 was actually focused in the Eastern Tropical Pacific in a low salinity area. And the goal of both SPURS 1 and SPURS 2 was, in a sense, connecting the physics also with, obviously, the remote sensing, the data from the SMAP and from the SMAP missions, but also connecting what was happening at the surface to the physics of what was driving these salinity changes in these 2 very, what I call very good examples, in terms of low salinity and high salinity, and what was driving actually the physics of those 2 different examples of changes in salinity in the ocean. And by the way, I want to say just up front, all of this data, again, is available, through the PO.DAAC. And another example, and I'll just mention this, is oceans melting Greenland. And OMG, again, this data is all available through the PO.DAAC. And this is this seminar is very timely, because it was just a paper that was released by also scientists Ian Finting and Josh Willis, who were co-authors on this. They were also scientists at JPL. And the basic issue was you have these 2 Greenland glaciers, but the melting is at different rates. So the atmospheric forcing is the same. So this is also a great example, because you're looking at the remote sensing data, from things like GRACE, and also that can actually look at the movement of mass on the ocean surface. So we had a good idea, okay, we can look at the melting of these Greenland ice sheets, and they were different, but the atmospheric forcing is the same. So what turns out to be the cause was the ocean melting Greenland, which was a series of in situ observations, in the Greenland, off of Greenland, showed that, in fact, there was water interacting with one of these glaciers that actually changed the melting rate. Again, this is an amazing conclusion, from an in situ data set. We could not have had this kind of information without oceans melting Greenland and connecting the effect of the oceans on the melting of a Greenland ice, of a Greenland glacier, and why there were differences when the atmospheric forcing was absolutely the same. So this is a great example also. The remote sensing, extremely important in telling us what was happening with respect to the changes in these glaciers in Greenland. But in terms of understanding the full physics, you needed the in situ data. And again, OMG is completely available also through the PO.DAAC. So I just wanted to stress, the importance of these data sets, SPURS 1, SPURS 2, OMG, again, in connecting what is happening that we know from the remote sensing data, but also connecting it with the physics, which is critical to understanding, in terms of issues like climate and other things. And the data set that I have come, recently, excuse me, I'm sorry. A data set that I have also been, recently very involved with was the Saildrone uncrewed surface vehicle. And, we call it autonomous, but I have to put a caveat. It's autonomous, but it's also a vehicle that can actually be guided from land. So you can actually tell it exactly where to go. And I also want to stress it's green technology in the sense of it's solar powered and also wind driven. Saildrone has multiple instruments on board that can measure everything from air-sea fluxes, in terms of wind speed. It can measure sea surface temperature, sea surface salinity, ocean currents, and also ocean chlorophyll. These are just some examples of the different kinds of measurements that Saildrone can actually look at. And again, we have, at the PO.DAAC, I just want to emphasize, we have measurements from 3 different Saildrone deployments, one in the Arctic, one off of Baja, California, and also the Atomic. There are other Saildrone deployments. Those are all the ones we have, obviously, at the PO.DAAC. We're also funded through NASA, and all of that data, again, is publicly available. And I'll show you some examples also of some, the science connection also with the validation. Again, Saildrone has proved extremely important because it's a vehicle that actually goes over the surface of the ocean, and it can be, it can actually do that for long periods of time. We can actually look at also what's happening, not just at one particular point, but also look at what's happening in terms of gradients. How is the ocean changing on a synoptic time scale over that period of time? So Saildrone is unique in giving us these, this information on gradients at the ocean surface. And why is that important? Again, it's extremely critical for understanding the air-sea coupling. So again, Saildrone has shown us has given back excellent results, and also from the validation perspective and also from the physics perspective. And I'll just go, Jennifer, to the animations. And I'll show you just quickly an example of 2 of the deployments. One was, this was off of Alaska. And you'll notice that, there are plots that on the left-hand panel and the right-hand panel, excuse me, the left-hand panel is sea surface, the left-hand panel is sea surface salinity from the remote sensing SMAP product, and the right-hand panel is sea surface temperature. And white is the Saildrone measurement, and red is actually the measurement from the satellite. The right is also at sea surface temperature from the remote sensing systems product that also is available through the GRIST project and also available through the PO.DAAC. But one of the things you'll see, and you'll see in the top panels the actual path of the Saildrone deployment. You'll see these, these low salinity components that you'll actually see around the May timeframe that are actually, visible in both the Saildrone deployment and also the remote sensing product deployment. And actually, in a paper that we just recently published, we actually examined those low salinity components off the Alaskan coast. The deployment was actually released, I'm sorry, backtracking, but the deployment was actually released from Dutch Harbor in Alaska and went northward. And when it reached the Yukon Delta is when you see these actually fairly large freshening events. So we're very excited in these results and being able to actually validate the remote sensing data, the SMAP data, and using this as a possibility of actually monitoring these river kind of discharges and off of Alaska and in the Arctic in this critical part of the world's oceans for understanding climate. So this was a very, excuse me, a very exciting result. And on the right, you also see the sea surface temperature overlaid with, again, remote sensing overlaid with the Saildrone data. And the amazing thing is you see this, what I think is just, incredible results in terms of the relationship and using Saildrone for validation purposes. When you look at these the kind of correlations and statistical relationships between Saildrone and the remote sensing data, we're getting very, very good correlations of 0.9 and above. So these results are very, very encouraging for using the SMAP data and also the SST data, again, in this critical part of the world's oceans. And you see, again, these differences in SST. You also see the sea surface temperature associated, with these freshening events. The river discharge actually from the Yukon actually, inputs warmer water off of the Alaskan coast, not colder water, but actually warmer water. So comparing, and this is also a very good example, the interdisciplinary, approach now and integrating data sets from different satellites with, in situ data. So this is another great example. And the next one will be, the next example will be from the atomic deployment, which was actually in the Caribbean and actually went into the area of the Amazon River outflow. And you can actually see, you'll be able to actually see very clearly the the low salinity waters associated with the Amazon River outflow. The low salinity waters off of the as the deployment actually, as Saildrone actually causes the Amazon outflow there or not. And then you can also see the sea surface temperature. Sea surface temperature is actually, now we use the higher resolution NASA Muir sea surface temperature product, and you can also see the changes in sea surface temperature associated with the Amazon River outflow. Oh, here we go. Now it finally came up. Okay. But this is also a great example of the, of using, this has also been major work done by Severine Fournier also at JPL, who's actually looking at, using SMAP data to actually monitor changes in in these river discharges in different places of the world's oceans. So this is another great example of using Saildrone actually also to validate, these changes in the river, as the changes in salinity due to river discharge also, and also changes in sea surface temperature. Again, I really want to stress the aspect of the multidisciplinary approach here and how important this is in looking both at sea surface salinity and also sea surface temperature, and also the uniqueness of Saildrone as one instrument that can actually, again, we can look at how these changes happen as, you cross the gradient, you cross these fronts associated with river discharge. And you can see that very, very clearly, in the time series. You can see the low salinity water, as Saildrone crosses the Amazon. And also you can see the changes in temperature also as the Saildrone crosses the Amazon. So I wanted to give an example. Those are 3 examples of in situ data that is actually all available, through the PO.DAAC. And we're also getting, software that's actually being used and developed also. I think that'll be part of what's coming up too in terms of co-locating, in situ data with remote sensing data to be able to look at, use it for in terms of validation, but also not just validation. Example, I really wanted to show the example of oceans melting Greenland. Also in SPURS 1 and SPURS 2. It's not just validation. It's also integrating what's happening at the surface with also, what's happening, underneath the surface. And that's where the in situ data, especially another great example from ONG, that's where the in situ data gives us a lot of information which we can't get necessarily just from the satellite. So again, a necessary partnership. Thank you. And I'll turn it back at this point. I'll turn it back to Jennifer. Thank you.
Okay, thank you, Jorge. At this point, we will transition to our final optional polling questions. We'll give these about 3 to 4 minutes, and then we'll transition to the question and answer period. I do have both of the animations are available for download. They're actually uploaded as separate files. And the PowerPoint slide deck is also available for download. So in just a few minutes here, you'll see that in the bottom right corner of your screen, you'll be able to highlight any of the 3 files and be prompted with an opportunity to download. All right, thanks everybody. Let's give this just a few minutes, about 3 more minutes, and then we'll transition to the Q&A. And if our speakers could remain muted during this time period, and then just okay, everybody, at this point, we're going to transition to the Q&A. And we have quite a few questions here, so you just give me a moment here. Okay, so several people asked about whether or not the presentation has been recorded. Yes, today's presentation has been recorded, and I will make the direct link and the YouTube link available to all registrants by Friday, if not tomorrow. The presentation files are available for download in the lower right corner of your screen. You should be able to see that. And let's see here. Wait just 1 second. Okay, so can we have access, this was during Ed's demo, can we have access to the LLC simulations MIT GCM through the cloud as well?
Not the LLC, if I remember my ECCO models correctly. I know there's very many flavors and different versions of ECCO. ECCO is a pretty large kind of scientific consortium. This particular one is, as I mentioned, is ECCO version 4, and it's a half-degree resolution. The LLC, I think, is significantly higher, maybe less than 1/10 of a degree, if I remember correctly, or somewhere on that order. That is not part of this particular data set release, and to be honest with you, I don't have a good answer to your question about if it's going to be accessible on the cloud in the future. I just know that it's not going to be part of the PO.DAAC catalog as of yet.
Okay, well, thank you, Ed. The next question is this SST DataCube notebook or something similar available publicly on GitHub or elsewhere?
Yeah, I apologize for that. I should have posted the link inside my presentation. And actually, if you scroll through the chat, several people asked about that and found it. So, and I'll post it in the chat here again in a second here, but it's on a publicly available GitHub site, as well as a number of other recipes. We probably have a collection of like 15 recipes written now to work with different types of data and stuff. And we've demonstrated those at things like the last fall HU. We just had a SWOT early adopters workshop where we developed another kind of a lot of exciting data recipes that show things like matchups, kind of like intersensor type recipes. So those are all available on this site for you to download, and they're all Python Jupyter Notebook. I'll post that link in the chat right now if I still have access to it. Yes.
Okay, thank you, Ed. The next question is, okay, there actually was a question just before this. Is there any explanation about the script use in the web page? I'm not actually sure where specifically this was referencing, if the user wants to provide a little bit more information. And then the next question, oh, go ahead, sorry.
Yeah, I don't understand that question either, but again, the only recipe that was shown was this Modus ARD data cube. Okay,
thank you, Ed. The next question is, can we download or order data using automated code from a cloud perspective?
Yes, the answer to that is definitely yes. There's I didn't demonstrate it, but there are CMR queries. So CMR stands for the Common Metadata Repository. You can execute queries on data that is in the cloud, and you can, by passing in the right parameters, you can get the most recent data. Actually, if you go in the presentation, I mentioned that there's some recipes just on Sentinel-6. If you exercise some of those, you'll see these capabilities of how to query collection for the most recent data.
Okay, thank you, Ed. You pasted the link into the presenter chat, so I've added it into the broader chat at this particular
Yeah, so
point.
that's the link actually to my little Modus data cube recipe. And if you just back up like one, just go to the notebooks folder, right, you'll see the whole list of other recipes, including the Sentinel-6 recipes that I just mentioned.
Okay, perfect. All right, just moving on to the next question here. Yeah, so as I'm looking for questions, it's helpful if try not to scroll through the questions because you're going to put me in a different location. Okay, so the next question is, okay, we've shared the Jupyter Notebook. Does the query work for an area inside a polygon?
The answer to that is yes. Yes, there are, you can pass in a polygon and even extract a polygon of information. And I think we have demonstrated that in some other recipes. Again, I guess there's two maybe questions in that. One, can you search for data that falls within a certain polygon? And the answer to that is yes. The extraction part, I believe, might be dependent on the processing level of the data set, but I think the answer to that is affirmative as well. So you can extract over a polygon. I know that we have demonstrated like extraction over things like shapefiles, right, where you pass in a polygon and extract only just part of what that shapefile that you need. So that is all possible using this Harmony and CMR cloud ecosystem.
Okay, thank you, Ed. The next question is, how generic is the level 2 gridding service in Harmony? For example, sounders, etc.
That's also another good question. Actually, I haven't experimented with sounders, but it should be pretty generic. Of course, we don't have any sounding data per se in our particular archive, but that shouldn't preclude it from being used by Harmony, but I guess I would need to go test that. Sorry, I don't have a good answer on that one.
Okay, thank you, Ed. We have just entered the extended Q&A period. Just a reminder, if we're not able to get to your question during the next 15 minutes, then our speakers will follow up with you offline. I will send them the Q&A log so that they're able to do so. The next question is, will the Sentinel-6 STC Level 2 data be available on the cloud?
Can you repeat that question again? Was it the Sentinel-6 data?
Yes. Will the Sentinel-6 STC Level 2 data be available on the cloud?
I think the answer is yes. I don't be honest with you. I'm not familiar with what STC stands for, but I mean, all the Sentinel products will be that are coming from the science data system will be archived and stored and distributed from the PO.DAAC, all the way going back to level 0. So I think the answer to your question is yes. And again, it's all going to be in the cloud, natively in the cloud, only available in the cloud.
Okay, perfect. Thank you, Ed. The next question is, can we subset multiple location, latitude, longitude data at the same time?
Multiple locations at the same time. I think the answer there is that in that example I showed, you can only pass one bounding box per Harmony query. So I think the answer to your question is if you have multiple bounding boxes, you would need to explicitly pass those in as separate Harmony queries. So the answer would be no.
Okay, thank you, Ed. I appreciate it. The next question is, can we validate remote sensing data with in situ data on Saildrone real-time on board?
I'll pass that one to Jorge.
Maybe that's a good question for Jorge.
Yeah, well, the answer to that is right now we're getting the information obviously after the data is processed, but I think the lag is a fairly short period of time. We might get the data within a month or something like that. But the answer is, can you do it in terms of near real time? Not in terms of the data that's coming into the PO.DAAC. We probably would have to ask directly, the data provider to see, about actually doing that kind of integration in near real time. But in terms of, have they done that? The answer is yes. They do look at the, part of Saildrone. The amazing thing about it is that, they can look at the satellite data in near real time during the deployment and actually, use the satellite data to guide where Saildrone should be going. So that is happening. In terms of accessing the data, that's a different issue right now, though.
Okay, thank you, Jorge. The next question is, how do we get the in situ salinity data? Is there a direct link? So although I placed the, PO.DAAC webpage in the chat pod, is there a more direct link? I'm sure there are some dataset landing page for specific products, but for the in situ salinity data.
Well, the answer to that is that, for example, salinity, a lot of the validation with matchups has been done with the Argo dataset. So Scripps is one of the providers of Argo that you can actually go to directly, to get that dataset. And you can use that obviously for matching up with the salinity data. The European Space Agency has its own system. I'm not familiar with it, but has its own system called PyMap and other systems for integrating matchup data set with remote sensing data also.
Okay, thank you, Jorge. Okay, so the next question is there bathymetric sediments, tidal, and wave power with high accuracy available from free sources? So I assume we're talking about bathymetry data, sediments, tidal, etc. I got a little tongue-tied for a moment. So can you speak to data set availability for bathymetry, sediment data, tidal and wave power at PO.DAAC?
There's no bathymetry data at the PO.DAAC. You have to go to other sources for that. eTopo 5 is one of the more, I'm not an expert in that, but that's one of the also bathymetric data sets that's used. But, in terms of data availability through the PO.DAAC, not that I know of, there's no, we don't distribute any bathymetry data.
But you do have, wave height data, right, at PO.DAAC?
Yes, we do have wave height data. Yes, we do.
But I'm not sure if that includes wave power. I'm not familiar with the specific potential data set here. And certainly, there are some ocean color data sets that could perhaps be used from our ocean biology DAC addressing sediment and so forth. And so I think with that, we can certainly follow up offline as well with additional resources. So why don't we go ahead and move on to the next question. Let me just give me a moment here. Okay, how do the Saildrones interact with ocean wildlife such as mammals, turtles, or birds? That's a great question.
Oh, wow, yeah, that's a fantastic question. Well, in terms of, Saildrone does have a fluorometer, an onboard fluorometer, which actually measures ocean chlorophyll. So the connection with the ecosystems and the biology would be through that particular measurement. It also, it does measure wind speeds. It also measures ocean currents also. So any connection between, wildlife and those physical measurements would obviously, Saildrone would provide valuable information in terms of that. Yeah. But in terms of direct measurements of specific wildlife, I'm not familiar with any kind of specific measurement on Saildrone that would do something like that.
And I'm not sure if maybe the participant was asking too whether or not there's any kind of impact to wildlife such as mammals, turtles, or birds. So if...
Oh, you mean, I'm sorry.
Yeah, I'm not sure. So if the user wants to provide additional clarification, that would be helpful. And why don't we go ahead in the meanwhile move on to the next question here. We've got about 6 minutes left. Can we get hardware and software details for Saildrone?
Well, Saildrone, in terms of hardware, for example, the deployment in the Arctic had 4 different kinds of four different kind of temperature sensors on board. You know, they were, 2 of them conductivity, temperature, and depth, what we call CTDs. They were on board. They also had radiometers on board. So there were 4 different measurements of sea surface temperature. Sea surface salinity, obviously, that's also a measurement that comes directly from the CTD instrument. There's also, measurements for ocean winds. Also, Saildrone has what they call an advanced Doppler current profiler. The ADCP is used to measure ocean currents. So those are just some of the, and again, as I mentioned, the fluorometer is used to measure ocean chlorophyll. So those are just some examples of the instrumentation on Saildrone. There are others. Those are the ones I'm most familiar with.
Okay, thank you, Jorge. The next question is, what will be the latency of the SWOT data for PO.DAAC?
Oh, wow, I don't know if Ed knows that. Ed chime in, or, based on experience with remote sensing data, what usually happens in these situations is during the calibration phase, or, you usually have, a period of time where the data is available within months maybe of processing. But also I think, that latency decreases, with the improvements in the processing of those particular data sets. So I would assume that if history repeats itself with remote sensing, that SWOT will eventually be available in near real time. But of course, the volume of the data, the new model and processing, but hopefully that'll actually improve, in terms of the capability of getting the data out in real time.
So the SWOT data, when it initially launches, there's going to be a cal-eval phase and a science phase. After that, after those phases are done, the SWOT data should be available with a 3-day latency.
Oh, fantastic. Thank you, Jessica. Thank you.
Did you say 3 days, Jessica?
It's nominally 3 days.
Yeah. I'm just looking here at the Sentinel catalog here, the Sentinel slide that I presented. And for example, Sentinel is going to have a 3-hour near real-time data set. So I would kind of expect that at least SWOT will have, something comparable.
Well, SWOT's a SAR. It's a different type of SAR instrument. There is a nadir altimeter, and the nadir altimeter data will be available within 3 to 5 hours.
Mm-hmm. Do they have an estimate of the whole cal-eval time period for SWOT?
It's 9. Well, the cal-eval phase is about 90 days, but that's after the checkout phase, and I don't remember how long that is.
Okay.
Okay, thank you, Jorge. Let me go back up here. Okay, so what are the requirements for the Jupyter Notebook tutorials? One of the participants has noted that he or she cannot open the notebook and is receiving a not JSON error.
Well, I think the requirements, I'm not sure about the error, maybe you can repeat that, but the requirements for the notebook are just kind of the Python version 3, of course, and I mean, there are other dependencies in there that I mentioned with regards to NCO and GDAL. Those libraries must be available as well. And there's some other Xarray. We use Xarray for the plotting. That's part of the Pangeo ecosystem. But yeah, I mean, I don't know what kind of package manager you use for things like Python, but Anaconda is very popular these days, where it's very easy to just go out on the on a tree and just install the the libraries and the dependencies you need and just be up and running within a matter of minutes. But Jennifer, can you repeat that error again? I understood something with JSON or something.
Not JSON.
Yeah, I would have to. I'm sorry, I can't answer your problem completely or your question completely. But again, if you are familiar with running Jupyter Notebook, it's pretty straightforward to install the dependencies and have these tutorials just run right out of the box. I saw another question in there about Docker containers, and that that's perhaps something we'll look at in the future and stuff.
Okay, thank you, Ed. We really have time for one more question, at least within the format of the webinar. And so the next question is, I'm just going in the order of how they were received. Hopefully I haven't missed any. Some of them were answered in the chat pod by our speaker. I don't know much about computer programming. Is there any data set that could be downloaded directly in an easy format to incorporate into stats and graphs tools, like an Excel spreadsheet? So I guess that's more of a question about the data sets and potential data formats.
Yes. If you wanted to do something simple for just extracting data into an Excel spreadsheet, perhaps you want to maybe look at the PO.DAAC service that we provide for our on-premise data. So here I'm not talking about the cloud data sets, but of course the majority of our data sets are still just on-premise spinning disk. There's a service called PO.DAAC where you can, all of our data sets are exposed on the PO.DAAC server. And it's basically a subsetting service again, but one of the outputs from PO.DAAC is a ASCII output. So that is then easily ingested into Excel. Typically use PO.DAAC to subset and output NetCDFs or HDFs, kind of sticking with the data format. But if you wanted to get it at ASCII, that would be usable in your Excel. In Excel, that would be one way to do it. You can contact me offline too. Just reach out and find me at Armstrong, and I can help you with that.
And so when I said and to thank our three speakers, Ed Armstrong, Jessica Hausman, and Jorge Vasquez, we appreciate your participation and your feedback. And our next webinar will focus on snow and ice data sets. It will be held, and also services and tools. It will be held on April 28th. At this point, we will log off from the audio component. However, I will leave the virtual meeting space open for another 10 minutes or so. There are a few questions I'll respond to, and then our speakers should be able to get back with you offline and address some of the inquiries we were unable to address during the time constraints of today's webinar. So thanks so much, everybody, and at this point we'll log off from the audio component, and I hope to see you at an upcoming webinar. All right, thanks, everybody.
Thanks
Bye-bye
all.
now.
Thanks, Jennifer, and everybody. Bye-bye.
You're welcome. See ya.
Thank
Bye-bye
you so
now.
much. Thank you.